There is a vehicle that bends in the middle, swims without warning, operates identically in -46 and +46 degrees, and somehow managed to get itself thrown out of one war while simultaneously being purchased by 6 different countries who could not get enough of it. This is not a story about a failed experiment. This is a story about a machine that was almost too good at exactly one thing, and what happened when the world asked it to do something else entirely. Hello everyone, and welcome back to the Mad Arsenal. Today we are covering the BvS10 Viking, one of the most capable and most contradictory military vehicles of the last 30 years. Stay with us to the end, because there is one detail about this machine that reframes everything that came before it, and we're saving it for last. To understand why the BvS10 exists, you need to understand the problem it was built to solve. Conventional tracked vehicles have a hard limit. Snow deep enough, mud soft enough, ground broken enough, and they stop. For armies operating in Northern Europe, that was not a theoretical concern. It was a practical reality every winter, in every exercise, on every piece of terrain that mattered most. The articulated two-section layout, 2 tracked hulls connected by a flexible joint, had been the answer to that problem since the 1960s. The principle was simple and brutally effective. Spread the weight across 4 wide tracks, let the 2 halves move independently of each other, and the ground that stops everything else becomes passable. By the late 1990s, that principle had produced one of the most widely exported military utility vehicles in history. More than 11,000 examples had been sold to more than 40 countries.
The machine worked. What it did not do was protect anyone inside it. It carried no armor, offered no survivability against anything more threatening than bad weather, and was entirely unsuitable for any environment where someone might shoot back. For peacetime logistics in the Arctic, it was adequate. For anything involving actual danger, it was not. The organization that felt this gap most acutely was the British Royal Marines. The Royal Marines had always operated in conditions that demanded exactly this kind of mobility. Contested beach landings, Arctic terrain, mountain approaches where wheeled vehicles gave up within the first 100 meters. They understood better than almost any other unit what it cost operationally when a vehicle got stuck in the wrong place at the wrong time. And by the turn of the millennium, they had been without any armored vehicle whatsoever for more than 50 years. When they needed to move troops under fire, they did it in soft-skinned vehicles or on foot. That gap produced a conversation between Hägglund's Vehicle AB, the Swedish manufacturer that had built the articulated concept into a global product, and the British Ministry of Defense. The brief that emerged from that conversation was demanding in a way that made most conventional procurement requirements look straightforward. The new vehicle had to carry protected troops across Arctic terrain. It had to swim. It had to operate in desert heat and Arctic cold on the same service contract. It had to be light enough to be airlifted, but strong enough to survive a mine strike. And it had to do all of this while preserving the low ground pressure that made articulated vehicles worth building in the first place. The vehicle they agreed to build was designated BvS10.
In Swedish, bandvagn skyddad 10, protected tracked vehicle 10. The British forces called it Viking. The first prototypes were delivered for evaluation in June 2001, and what followed across the next 2 years would test every claim the specification had made about what this machine could actually do. What the evaluation teams discovered was that the BvS10 was not one vehicle with several useful features. It was several entirely different capabilities packaged into a single hull, and each of those capabilities had a story attached to it that no test range had fully anticipated. Those stories are what this video is about. The articulated joint at the center of the BvS10 is not a passive hinge. It is a hydraulically controlled assembly that works in 2 planes simultaneously.
bending the two hulls vertically when the ground rises and falls, and laterally when the driver needs to change direction. Steering does not work the way it does in a conventional tracked vehicle, where one track brakes while the other drives, and the whole machine pivots around the slower side. In the BvS10, both tracks on both sections continue to drive throughout every turn. The hydraulic rams simply push the two halves against each other, bending the whole assembly around the joint, like a lorry bending around a corner. Except that this lorry weighs 10 tons, carries armored troops, and does it equally well on ice, sand, and open water. That last surface is where the design produces its most unexpected result. The BvS10 is fully amphibious. Not amphibious in the sense of being able to cross a shallow ford without flooding the engine bay. Genuinely amphibious, capable of entering open water and propelling itself across it using nothing but the rotation of its 4 rubber tracks against the surface. Water up to 1.5 meters deep can be crossed without any preparation at all. For deeper water, full amphibious operation requires less than 2 minutes of preparation, sealing hatches and activating the bilge systems. The vehicle reaches speeds of up to 5 kilometers per hour on the surface, which is not fast, but is fast enough to cross a river, negotiate a flooded estuary, or come ashore from a landing craft without the crew needing to find a dry route.
For the Royal Marines, who had spent 50 years without any armored vehicle, and whose entire operational identity was built around amphibious assault, this was not a secondary feature. It was the reason the vehicle existed. The ability to launch from a ship, cross open water, and come ashore under armor, without preparation, without specialist equipment, without waiting for conditions to be perfect, was precisely what beach assault operations demanded, and precisely what every previous armored vehicle the Corps had considered could not provide. The trials in 2001 and 2002 confirmed what the engineers had calculated. The vehicle entered water cleanly. The articulated joint remained functional while both sections moved independently on the surface, and the transition from water to land required no pause and no reconfiguration. A crew that had trained on the system could go from dry land to open water to dry land again without stopping, without getting out, and without touching anything beyond the controls already in front of the driver. What nobody in the trials program had scripted was how this capability would eventually be used. The scenarios on the test range involved beach landings and river crossings in Northern Europe, the environments the Royal Marines trained for and expected. The reality turned out to be considerably stranger. In July 2011, a landing craft was launched from RFA Cardigan Bay, a Royal Fleet auxiliary vessel operating in the waters off the Horn of Africa. The craft carried 2 BvS10 Vikings and a small team of Royal Marines from 539th Assault Squadron. They came ashore in Somaliland, the self-declared territory in the north of Somalia, and drove several miles inland through territory that local knowledge described, with considerable understatement, as bandit country. There were no safe roads. There was no friendly force waiting to meet them. There was a clan chief who needed to be collected and brought back to the ship for a meeting with MI6 and Foreign Office officials as part of an operation to establish relationships with tribal leaders and support anti-piracy efforts in the region. The Vikings crossed the water, came ashore, drove through hostile territory, collected the clan chief, and returned. The operation was later reported in the British press, which is the only reason it exists in the public record at all. 2 armored, articulated vehicles had launched from a warship, swum to a hostile coastline, penetrated miles of dangerous ground, completed an intelligence mission, and returned to the sea. Every step of that sequence depended on the amphibious capability and the articulated mobility working together as a single system. A wheeled armored vehicle could not have done it. The terrain would have stopped it before it reached the objective. A conventional tracked vehicle could not have done it.
It could not have come ashore from the landing craft and crossed the water independently. What made the operation possible was precisely the combination of features that had made the BvS10 look over-engineered to anyone who had only ever imagined it operating on a Norwegian training range. The same joint that allowed the two hulls to flex over broken Somali ground was the joint that kept the vehicle stable when transitioning between water and land.
The same wide rubber tracks that distributed weight on soft terrain were the tracks that propelled the vehicle across the surface of the water. The amphibious capability and the cross-country mobility were not two separate systems bolted together. They were expressions of the same underlying design principle, and in Somaliland, they worked as one. There is also the matter of air transport. If the operation had required the Vikings to reach a location inaccessible by sea, the two sections of each vehicle can be separated in approximately 20 minutes, each half light enough to be carried individually by a Merlin helicopter. A 10-ton armored vehicle that disassembles for helicopter delivery and reassembles in the field is not a standard feature of any procurement catalog. For the Royal Marines, whose operations regularly take them to places where no road, no landing strip, and no heavy transport can reach, it was simply one more expression of the same logic that had produced the vehicle in the first place. Most military vehicles are designed for a climate. The assumption is built into every component choice, every fluid specification, every material selection. The engineers know where the vehicle will operate, and they optimize accordingly. Arctic vehicles use cold-weather lubricants. Desert vehicles use heat-resistant seals, and the two categories rarely overlap in any meaningful way. The BvS10 was designed around a different premise entirely. The temperature range written into the specification, from -46 to +46 degrees Celsius, was not a marketing claim. It was an engineering requirement, and it meant that every single component in the vehicle had to function across a span of 92 degrees without modification, without special preparation, and without asking the crew to swap out any part of the system depending on where they happened to be deployed. The Cummins turbo diesel at the heart of the vehicle had been chosen partly because its engine family had already proven itself across exactly these extremes in civilian applications. Construction equipment in Scandinavian winters, marine engines in tropical waters. Adapting it for military use in a vehicle that needed to start reliably at -46 and not overheat at +46 required careful calibration, but the fundamental architecture was already validated. The hydraulic systems controlling the articulation joint presented a harder problem. Hydraulic fluid that flows correctly at Arctic temperatures becomes dangerously thin at desert temperatures, and fluid that works in the desert can become too viscous to operate the rams at extreme cold. The solution required fluid specifications and seal materials that held their properties across the full range, an engineering constraint that added complexity and cost, but was non-negotiable given what the vehicle was being asked to do. The evaluation teams decided the only honest way to test this claim was to do exactly what the specification promised. In the first phase of trials, the vehicles went to Norway, operating in winter conditions that produced the kind of cold that makes diesel engines reluctant and hydraulic systems sluggish. The articulated joint moved, the tracks gripped, the engine started. The vehicle performed across snowfields and frozen terrain with the confidence the design had promised. Then, in September 2001, the same vehicles were transported to Oman for exercise Saif Saria, one of the largest British military exercises in decades, conducted in one of the harshest desert environments available. The contrast was not gradual. The same machines that had been operating on Norwegian snow were now sitting in Omani heat, breathing air full of fine sand that works its way into every gap in every component and grinds against every moving surface it reaches.
The rubber tracks that had floated across soft snow were now in contact with rock and compacted desert floor. The hydraulic fluid that had been flowing through the articulation joint in sub-zero temperatures was now being asked to do the same job in air temperatures that challenged the cooling system's limits. The BVS10 handled both. Not identically. No vehicle performs exactly the same across two environments that different, but the fundamental capability held in both directions. The articulated joint kept working. The engine kept running. The tracks kept gripping. The evaluation teams, who had been specifically looking for the point at which the temperature range claim would break down, did not find it within the bounds of either trial. But the Oman trials revealed something the Norwegian trials had concealed, and it was not a flaw in the vehicle. It was a flaw in how people were thinking about it. The BVS-10's defining advantage, the articulated layout, the low ground pressure, the ability to cross terrain that stopped everything else, was only relevant when the terrain actually needed crossing. In the desert, on flat, hard ground, the vehicle moved adequately and no better than several conventional alternatives. Its top road speed of up to 70 kilometers per hour was respectable, but not exceptional. Its protection was modest. Its armament was minimal. On the test ranges of Oman, where the ground cooperated and the obstacles were manageable, the BVS-10 was a competent vehicle among several competent vehicles. The implication was clear to anyone paying attention, though nobody chose to say it directly in the assessment documents. The BVS-10 was not universally superior. It was specifically superior, dominant on terrain where the ground itself was the primary obstacle, and merely adequate everywhere else. That distinction would matter enormously in the years ahead, in ways that the evaluation teams in Oman in 2001 could not have predicted. What the trials did confirm, unambiguously, was that the temperature range specification was real. The vehicle that had started reliably in Norwegian winter started reliably in Omani summer. The articulation joint that had bent over frozen terrain bent over desert rock. The rubber tracks that had distributed weight on soft snow distributed weight on soft sand. For procurement officials evaluating a vehicle that might be deployed anywhere from northern Norway to the Persian Gulf on the same contract, that consistency was the most valuable thing the trials had demonstrated. The British Ministry of Defence signed the production order. The first vehicles were delivered to the Royal Marines in July 2003. Initial operating capability was declared in 2005. A vehicle designed for Arctic warfare had just been accepted into service by a military that was about to send it somewhere neither the designers, the procurement officials, nor the evaluation teams had seriously considered. The protection philosophy behind the BVS-10 was not an accident or a compromise forced by budget constraints. It was a deliberate engineering decision based on a specific operational theory. The vehicle was designed to survive through movement rather than armor, to be in the wrong place before the enemy could target it, rather than to absorb the hit when it arrived. The base protection resisted 7.62 millimeter armor-piercing rounds and artillery fragments from distances greater than 10 meters. Additional bolt-on armor packages could be fitted in the field for higher threat environments. The vehicle was rated against anti-personnel mines with charges up to half a kilogram. That last characteristic deserves particular attention because it connects directly to the articulated layout in a way that is not immediately obvious. The BVS-10 weighs 10 tons fully loaded, but spreads that weight across 4 wide rubber tracks 620 millimeters across. The resulting ground pressure is roughly equivalent to that of the lighter BV206 it was partly derived from, a vehicle 4 tons lighter. In practical terms, the BVS-10 pressing down on the ground feels, to a pressure-activated trigger buried in the soil,
like a much lighter vehicle passing over it. Most conventional anti-tank mines are calibrated to detonate under vehicles significantly heavier than their ground pressure suggests. The BVS10, almost as a side effect of the design choices that gave it Arctic mobility, was naturally resistant to a whole category of buried explosive threat. When the Royal Marines deployed 33 Vikings to Helmand province in the autumn of 2006, that characteristic worked exactly as described.
The low ground pressure was not sufficient to trigger most of the conventional anti-tank mines that Taliban forces had placed in the soil of southern Afghanistan. Vehicles that would have detonated those devices simply by driving over them passed through without incident. The engineers had not designed this capability intentionally for the Afghan environment. They had designed it for Arctic terrain, but the physics did not care about intent. The mine resistance was real, and it worked. What the Taliban had in Helmand, however, was not primarily conventional mines. The improvised explosive device, command detonated by wire or radio signal, triggered by pressure plates calibrated for foot traffic rather than vehicle weight, or activated by infrared beams that the vehicle interrupted simply by existing in the wrong place, operated on principles that had nothing to do with ground pressure. The size of the explosion was the only relevant variable. Devices containing 20, 30, or 50 kilograms of explosive, buried beneath a dirt road, did not care how lightly the vehicle trod. They detonated when triggered, and the light armor that was the deliberate price of the BVS-10's mobility was not built to absorb that kind of energy. Several Vikings were destroyed. Crews and passengers were killed. The operational theory, survive through movement rather than armor, functioned in the environments it had been designed for, where the threat could be outmaneuvered and the terrain itself was the primary obstacle. In Helmand, on flat roads, moving at predictable speeds between predictable destinations, there was no terrain to exploit and no maneuver that changed the equation. The vehicle was being used as a regular personnel carrier on regular roads, and for that role its protection was inadequate against the specific threat that had evolved to meet it. The British Ministry of Defence faced the result directly. In October 2008, less than 2 years after the first operational deployment, the announcement came that Vikings would be withdrawn from the forward fight in Afghanistan and replaced. The replacement was a heavier, more heavily armored articulated carrier purchased through an urgent operational requirement, the procurement mechanism that exists for situations where normal timelines are incompatible with keeping soldiers alive. Around 100 vehicles were ordered at a cost of £150 million. British forces called their version Warthog. The Warthog performed better against the IED threat. The heavier armor absorbed energy that would have destroyed a Viking. At least one vehicle survived a strike by a device estimated at 50 kilograms. The protection worked. But the Warthog was not amphibious. The additional armor that made it survivable on Afghan roads had taken care of that, and it was mechanically less reliable than the vehicle it replaced, procured quickly and without the full support infrastructure that sustained service requires. It was a more survivable vehicle in one specific environment, optimized for exactly the conditions that the BVS-10 had never been designed to face. After British forces withdrew from Afghanistan, the Warthog fleet was retired. The Vikings came back. A contract was placed to upgrade 99 BVS-10 vehicles to Mark II standard, adding a V-shaped underbody designed to deflect explosive energy away from the crew, improving braking and suspension, and restoring the full amphibious capability that the Afghanistan modifications had compromised. The upgrade was completed in April 2016. The machine that had been found inadequate for one specific war returned to the force it had been built for, doing the job it had been designed to do. The Afghan episode had revealed something that the trial program in Norway and Oman had suggested, but not stated plainly. The BVS-10 was not a vehicle for every war. It was a vehicle for a specific kind of war, the kind where terrain is the enemy, where mobility is survival, and where the ground itself has to be defeated before the human threat can even be engaged. Send it somewhere flat and predictable, and its advantages disappear. Send it somewhere broken, frozen, flooded, or unreachable by anything else, and nothing in the inventory comes close. The modular design of the BVS-10 was never presented as its headline feature. The amphibious capability got the attention. The articulated mobility got the engineering coverage. The temperature range got cited in every procurement document. But the modularity, the ability to reconfigure the same vehicle between roles without rebuilding it, to fit different armor packages, weapon mounts, communications systems, and interior arrangements, depending on the mission, was the characteristic that determined how widely the platform could spread and how long it could remain relevant. A troop carrier variant held 2 crew and 10 passengers. A command vehicle replaced the passenger fit with enhanced digital communications equipment. A repair and recovery variant equipped the rear section with specialist tools and a modified interior for 4 vehicle mechanics. An ambulance variant reconfigured the same rear section for medical treatment. A mortar carrier mounted an 81mm mortar in the rear hull. The exterior accepted bolt-on armor packages that increased protection against armor-piercing rounds at the cost of some mobility. Remote-controlled weapon systems could be integrated above the front cab for crews who needed to engage targets without exposing themselves. Every one of these configurations used the same hull, the same drivetrain, the same articulated joint. The platform did not change. Everything built on top of it could. That flexibility is what allowed the BVS-10 to accumulate operators in a way that few armored vehicles manage. Each country that evaluated it found a different mix of variants that suited their specific requirements, and the platform accommodated all of them without fundamental modification. The Netherlands Marine Corps took 74 vehicles in 4 variants: troop carrier, command, recovery, and ambulance, and deployed them first to Chad and then to Afghanistan, where slat armor packages were added in the field without requiring factory work. Austria ordered 32 armored personnel carrier variants with a 360-degree infrared observation system and remote weapon station, configuring the platform for mountain operations in a way the original Royal Marines specification had never anticipated. Then France made a decision that surprised almost everyone watching the market. In December 2009, the French Armed Forces ordered 53 BvS10 vehicles, with a total order reaching 129 machines at a contract value of around £220 million. The French designation was VHM, Véhicule à haute mobilité. France had a domestic option available and chose not to take it. The evaluation had concluded that the BVS-10 was the better vehicle, and national preference finished second. It was the first French order for military equipment from the United Kingdom in decades, and it happened because the modular platform had been configured to meet French operational requirements in ways the competing design could not match as cleanly. The most structurally interesting sale, however, was not to France. It was to Sweden, the country where the articulated vehicle concept had originated, where Helmand had built the BV206 into a global product, where the engineering lineage of the BVS-10 had its roots. Sweden had not initially ordered the vehicle for its own armed forces. While the platform was being sold to Britain, France, the Netherlands, and others, the Swedish military continued operating the older BV206 family domestically. In January 2012, more than a decade after the first BVS-10 entered service elsewhere, Sweden finally placed its own order.
48 vehicles under the Swedish designation BV410, worth approximately 700 million Swedish kroner. A further 105 machines followed in 2013. By 2021, the total Swedish orders had grown to several hundred vehicles across multiple contracts. Sweden then found a use for the BV410 that nobody had written into the original specification. In 2019, the Eldenhet 98 surface-to-air missile system was mounted on the BV410 chassis, replacing an obsolete air defense platform and giving Sweden a mobile missile launcher that could follow armored formations across exactly the terrain where wheeled air defense vehicles could not operate. A personnel carrier had become a missile system. The articulated layout designed for Arctic logistics was now part of Sweden's air defense network. In August 2022, the United States Army and National Guard selected the BVS10 Beowulf, the unarmed export variant carrying up to 14 people or 8 tons of cargo, under the Collaborative All-Terrain Vehicle Program, a common acquisition initiative among NATO nations to replace aging Arctic carriers. 110 vehicles were ordered at $278 million. The U.S. Army had evaluated the available options and selected a Swedish-designed articulated carrier. For a procurement system that historically favors domestic solutions, that outcome reflected clearly where the BVS-10 stood relative to everything else in the market. And then the vehicle that had been designed for Norwegian fjords and Scottish coastlines ended up in Eastern Europe. Prior to March 2023, the Netherlands donated 28 of their BVS-10 vehicles to Ukraine. In December 2023, the United Kingdom announced the donation of 20 more. Armored articulated carriers built for beach assaults and Arctic operations were now moving across the broken, waterlogged ground of an active land war, doing exactly what the articulated layout had always done, in conditions that proved, again, that the ground itself remains one of the most reliable obstacles in any conflict. The detail promised at the beginning of this video is this. The BVS-10 carries no serious offensive weapon, defeats no tanks, and was found inadequate in the one major war it was sent to fight. It was replaced in Afghanistan by a heavier vehicle purchased in a hurry from Singapore. Sweden took more than a decade to buy the platform its own engineers had helped create. And yet, it has been in continuous operational service for nearly 20 years across 4 continents, selected independently by the armed forces of Britain, France, the Netherlands, Sweden, Austria, and the United States, used to ferry intelligence officers through African bandit country, and donated to an active war in Europe. The BVS-10 was never the most powerful vehicle on any battlefield it crossed. It was simply the one that could reach places where everything else had already given up.
In a world where the ground is often the first enemy, that turned out to be a more durable advantage than armor, firepower, or speed. If this story was worth your time, leave a like, drop a comment with whatever piece of unusual military hardware you want covered next, and subscribe to the Mad Arsenal so you do not miss what is coming.